Hi everyone. So I'm gonna do this further mechanics question. It's from further mechanics 3 mechanics 3 and it's 8 of possibly. So yeah, let's start the question. So they give it's a question regarding a light elastic spring. Okay, let me just go through the question. They say an light elastic spring has natural length, blah blah blah. Okay, modulus, and then we get the angle. They say initially P is held at point B of the plane where AB is a line segment. Oh my god, what am I saying? AB is a line of greater slope of the plane. I've just been doing so many questions, so we're making a whole bunch of videos. So this is like, sorry, these questions are big, right? Take a lot of time. So yeah, I just got my head messed up. So I might make a few silly mistakes here and there, but I'll be rechecking them again. And finally, yeah, I'll be getting the correct answer. So yeah, and if you guys have any doubts with what I'm doing with the solutions, please drop them in the comment section. And if you like my video, subscribe and leave a like. Yep, so let's get on with the question. So they say the point B is lower than EEP equals 2L. The particles released from rest at B, and first comes the instantaneous rest at the point C on EB, where AC equals 0.7. Use the principle of conservation of mechanical energy to show that lambda equals 100/9 to 1 mg. So that's the modulus of elasticity. So we gotta find that now. Okay. So what you do is first comes the instantaneous rest. Okay, and it's released from rest too. Okay, so it's gonna be change in kinetic energy plus change. And since we have elastic potential energy, we have to consider that too elastic. That's how we find lambda here. Plus or minus potential energy, which is mgh. Because it's plus or minus, if it goes up, it's plus. If it goes down, it's minus, okay? And they don't say anything about resistance. They say it's a smooth plane, so this equals to 0. These are our energies we have to focus on. So let's find the answer. So change in kinetic energy 0, right? Because it was released from rest. And they say it first comes to instantaneous rest at point C. So we don't have to care about kinetic energy. That's 0. 0 plus. And elastic potential energy is lambda x squared over 2L, right? And it's going to be change. So you can write delta plus, and it's going up, right? It's going up. So plus mgh equals C. Okay. So now what we do is, let's write lambda final. So change. It's going to be final minus initial, right? So lambda x squared. So this time AC is 0.7. Okay, it's 0.7 L. So 0.7 L. So it's above the natural length. The natural length is L. And comes to instantaneous rest at the point C on AB, where EC is 0.7 L. Okay, I didn't see this in the question. They say it's a spring. Light elastic spring. So in case of a spring, so springs have extension and compression both. Right? We have both. I think I mentioned string earlier. I wasn't reading the question. I told you, but I'm sure I'll be making a few silly mistakes here and there. But I'll be getting the correct answer. So don't worry about that. So it's a spring. So if it's a spring, you have compression and extension both. So even though it's way past, way before its natural length, we still have to consider it. So it's going to be lambda into x is going to be 0.7 minus 1, right? So you can write like this 1 L. You can write L minus natural length is L minus 0.7 L squared over 2L minus lambda. Good, this is final. Now we are talking about, now it's initial, which is 2L minus L squared over 2L plus MGH. So it has went from 2L to 0.7L. So I'll just draw a small diagram. So let's say it's here. This is C. And initially it was here. So this distance is 2 minus 0.7, right? Just 1.3. And the angle is theta. So this distance is 1.3 L. So 1.3 L sine theta is a height, right? So tan theta equals 5 over 12. Sine theta is 5 over 13, right? So it's like this. Theta opposite side, adjacent side, 5 squared plus 12 squared is 169. So this is 13. So sine theta is 5 over 13, right? So this is going to be plus mgh equals 0. So let me just simplify the elastic potential energy. 1 minus 0.7 squared, you use 0.09 lambda. This into L minus L lambda over 2 plus m g 1.3 L into 5 over 13 equals 0. L cancels off, and you have 0.09 divided by 2, giving you 0.05 minus 0.5 lambda. So I'll put them in brackets, because you can take lambda out, plus 1.3 into 5 over 13, giving you 0.5 mg equals to 0. So lambda, so 0.05 minus 0.5 is 0.455. So it's minus 0.455. So I'm taking it to the other side. So now lambda equals 0.5 mg divided by 0.455, giving you 100 over 91 mg. So we got it, right? We got the answer for the first part. And then for part B, they say find the acceleration of P when it's released from rest at P. Okay. So for the acceleration, I'll draw a small diagram. At point B, so we have the tension acting upwards, mass acting downwards. This is your angle theta. So it's gonna be God, what's wrong with this? Okay. So it's gonna be T minus mg sine theta equals md, right? So T minus mg sine theta was 5 over 13 into md. And to find the tension, you know tension equals lambda x over L. So x is the extension, and lambda we found 100 over 91 mg into 2L minus L, because they're asking at B, over L. So this gives you T equals 100 over 91 mg. So it's 100 over 91 mg minus 5 over 13 mg equals ma. You can cancel off m. So you end up with 100 over 91 minus 5 over 13, giving you acceleration of 5 over 7 g. That is your answer. I hope you all understood this question. If you guys have any doubts, just drop them in the comment section. And if you guys like my teaching, leave a like and subscribe. And I also want to tell you guys that it takes me a lot of time to make these videos, to edit all that stuff. So it would be great if you guys could leave some support if you guys like my channel. And yeah, thank you so much. Have a great day. Yep.